Recording is beginning. Okay, got it.
You need to accept that.
Okay, great. Are we okay? Shall I continue?
Yes.
Okay. So since we just turned on the recording, let me repeat myself for a moment. My name is Matt Sievert, assistant professor from New Mexico State University. In this opening lecture, my goal is to sort of recap or build perhaps the foundation so that we can discuss what is the meaning of the theory of quantum chromodynamics, or QCD. I want to ultimately build the technology so that we can discuss in detail what do all of these words mean. What does it mean to be a gauge theory? What does it mean to be a non-abelian gauge theory? And what does it mean to be the particular gauge theory of SU3? That's my first 1 to 2 lectures. The rest of the week, I'll be talking about the high energy limits of QCD, the behavior of a scattering process in the limit when the center of mass collision energy E goes to infinity with the amount of transverse momentum that you exchange fixed. This is the so-called forward scattering limit, where if I take the energy to infinity but the transverse momentum constant, then that means that forward scattering angle, which is roughly ET divided by the energy, goes to 0 in this limit. So this is the forward scattering limit, sometimes called the Reggie limit. And this is deeply related to the physics of small x, if you're familiar with what that means, small Bjorken x. And this is what leads directly to the very important predicted theoretical effect called gluon saturation. And you may have also heard words associated with this, like the effective theory called the color glass condensate. So this is my charge. This is my goal for the week, is to sort of discuss foundations of QCD and how the limit of high energies reveals important properties of that non-abelian field theory. This has connections with the other lecturers who will be speaking with you this week. Thomas Lappi is a credible leader in the field of high energy and small x physics. Thomas and I discussed ahead of time, and he's going to talk about sort of the second half of this, how the physics of gluon saturation may appear in heavy ion collisions and other observables. And he's going to let me cover sort of the basics of where it comes from. If I recall correctly, I believe the other speaker, Thomas Becker, is going to be talking about effective field theories in general. And this color glass condensate, so to speak, is precisely an effective field theory, the effective field theory of how QCD behaves in the limits of high energies. So I think there will be nice overlaps between the foundations that I will try to give you here, the applications that Thomas Lappi will show you, and the general discussion of effective field theories. It may not necessarily all come in linear fashion, but as Heribert said, hopefully by the end of the week, all of these different threads will tie together and give you a complete picture. So that's the purpose, that's my goal.
Hi, I have a question.
Yes, please.
So with the diagram that you've drawn over there, where it's an arrow of E going off, which is scattered by an angle theta.
Yes.
And transverse momentum is kind of indicated as the opposite side of that angle.
Yes, here. The PT, that's correct.
Yeah. I don't see how when theta goes to 0.
Sure, yeah, let me illustrate it a little bit better. So in more detail, what I have in mind is that my incoming particle is, for the sake of simplicity, let's say everything is massless, so that the energy of the particle is E, and its momentum is, let's say, E along the Z direction. I'll write that as E k hat. And then after the scattering, my particle scatters off with some P prime, which has let's say approximately the same energy, and it scatters in some different direction n hat. The point is that this angle theta is related to that change in direction. And let's see, the amount of PT, I guess what I mean to say is here, the amount of energy is E, and then I pick up, in addition to the Z direction, which is E k hat, maybe this is how I should say it, E k hat plus ET vector. So I have some certain amount of Z momentum, which is this more or less the same as the original energy E, that's all going down the Z axis. And then I have some particular transverse components here. So the sides of this triangle, loosely speaking, are, if this is the angle theta, then PT is that transverse side, E is the longitudinal side, and then the hypotenuse, if you like, is square root E squared plus PT squared, but this is very close to the original energy. So why does the angle go to 0? Because on this triangle, sine of theta, or even better, tangent of theta, is PT over E. And in the physical limit that I'm interested in here, I want to take the numerator constant, but I want to take the denominator to infinity. So this is a limit where the opposite side of the triangle is fixed, but the adjacent side is getting extremely long. And that means that that angle of the scattering is tending towards 0. So I don't know if this answers the question, but this is more of what I'm trying to say, that the longitudinal momentum, where the energy is getting really large while the transverse momentum is fixed. And then just by the geometry of that triangle, that means that the angle is going to 0. Does that answer the question?
Yeah, it does. Thank you very much.
Okay, very good. Okay, so I wanted to start with something of a bird's eye view about what quantum field theory is and where it comes from. But as I started to take that bird's eye view and zoom out further and further and further, I eventually realized that I had taken sort of an orbital view of the entire process looking down from space. And I think that's where I want to start now, to talk about where does quantum field theory come from? Why is that the right language to use to try to describe QCD, and what does that mean for us? So my apologies if I'm starting a little bit too basic. My apologies if I'm going a little bit too fast. But I wanted to show the connections all the way from day 1 of working in physics up to day N of doing research at the frontiers of nuclear physics. So with apologies, I wanted to start from the very top. So starting with the formulation of classical mechanics, Newton, Lagrange, and Hamilton. So the very first thing that all of us learn as physicists, the very first description of how dynamics is encoded, is Newton's second law. I always abbreviate that as N2L. Newton's second law, of course, is F equals ma, our first kindergarten physics, as my PhD advisor would have called it, that tells you how the external forces that govern a system cause the dynamics to change in response. This is really pretty elementary. You can make it look a little bit more sophisticated if we write the force in terms of a potential. We write the force as the negative gradient of some potential energy. And I write the acceleration as the derivative of the velocity. And I write the momentum as mass times velocity. So that when I combine these two things together, mass times acceleration is the same thing as the derivative of the momentum. So it's still just F equals ma, but I can maybe point out a little bit more of the structure of Newton's equations if I express everything in terms of the position vector r and the momentum vector p. So if I put these two pieces together, then I have F equals minus gradient of the potential, which is equal to the time derivative of the momentum. Or in other words, the time derivative of the momentum plus the gradient of the potential energy should be equal to 0. So this is Newton's equation of motion. The thing that I want to point out about this, which is maybe not so obvious, is that Newton's equations pick out as special or privileged 2 specific variables in the problem. Those 2 variables are the position vector r. Where does the position enter? It enters right here because this is the gradient with respect to r of u. So you might say that this is the derivative of u with respect to the vector r. So position enters here, momentum enters here. And the connection between them is the expression for the momentum itself, which is P equals m r dot. So Newton's equations are a perfectly fine expression of the physics, The problem is that they leave much of the physics implicit. This is a complete description of how forces lead to changes in dynamics, but it leaves hidden information about other conserved quantities, things like angular momentum, for instance, not explicitly here in Newton's laws. That's part of what is such a major advantage in generalizing beyond Newton's equations to Lagrange's equations. Lagrange's equations formulate the dynamics in terms of the Lagrangian L. Usually that's written as T minus V, where T is the kinetic energy and V is the potential energy. So I guess for consistency, I should call this U, since I called it that a moment ago. In Lagrange's formulation, the equations of motion are more general. They don't rely only on this particular coordinate and this particular momentum. They preserve the same structure, but they generalize it, such that the Euler-Lagrange equations give you time derivative of this funny combination, derivative of the Lagrangian with respect to Q dot, minus derivative of the Lagrangian with respect to Q is equal to 0. This is sort of a funny looking equation, but if you stare at it for a second, you realize that structurally it looks exactly like this one. And in fact, if I pick my arbitrary coordinate, my generalized coordinate Q, if I pick Q equals the position vector, I get back Newton's second law right away. So if my Lagrangian is 1/2 m r dot squared plus, minus some potential v of x, u of x, then the derivative of the Lagrangian with respect to r dot is mr dot. This is just the momentum p. And then Lagrange's equations tell you the time derivative of the momentum minus the derivative with respect to the position x, so that is now plus derivative of u with respect to x, is
Probably want to say R.
yes.
You wanted to say R instead of X, I guess.
Sorry, say again. Oh, r. Thank you. Yes. If I want position vector r. Yes, thank you. Yeah. So the point is that this immediately recovers Newton's second law, but more generally. Why is it more general? Because it frees us up from being linked to the specific coordinate Q equals R and the specific momentum E vector. The key idea of Lagrange's equations is that the position vector and its momentum are not unique. They're not special. They are a special pair. They have a special relationship to each other. But any variable Q with its appropriately defined momentum will have the same fundamental relationship. So the point is that Lagrange's equations, Lagrange's formulation of mechanics, is it generalizes the idea of what a position and a momentum. Generalizes the idea of position and momentum. In particular, the thing that plays the role of momentum is that funny derivative of the Lagrangian. Derivative of the Lagrangian with respect to the velocity q dot. So this is the generalized momentum. And we say that it is conjugate to the coordinate q. So the point is that Lagrange's equations take the key ideas that were present in Newton's laws and they extend them in a way that generalizes the idea of position and momentum. So that I can take these equations and reduce them back to Newton's laws. Or I could take a different set of variables, let's say the angle theta and its canonical momentum defined by this relation, which is the angular momentum. So I can describe using Lagrange's equations in one step the physics of any variable that I choose because it extends that idea of what is a canonical momentum pair. As another comment, the thing that's perhaps so elegant about Lagrange's equations is that it formulates classical mechanics as a minimization problem. So why is Lagrange so nice? Because it basically takes all of physics and it turns it into a minimization problem. Because if I start with the Lagrangian and I integrate it over time, this integrated quantity known as the action is stationary, so that is its derivative is equal to 0 along the classical path. So essentially what that does for us is, if I know the equation of motion for my theory, I can always define an action such that the correct answer is the minimum of the action. That's really what we're doing. Most of the time you can write down your Lagrangian and take it to be t minus v or t minus u. Doesn't always work though. In particular, it doesn't work for the electromagnetic field. In those cases where it doesn't look like t minus v, what is your Lagrangian? The answer is your Lagrangian is whatever it has to be, such that when I minimize the action, I get back the correct equation function. So the Lagrangian can be whatever function I need it to be, as long as I make sure that physics, the correct equation of motion, is the minimum of the action. So that's why it's so general, is that it's not in reference to a particular set of coordinates anymore. The principle is generalized to minimizing this function called the action. And that's now coordinate independent. Any questions so far? Why am I belaboring this point? Because this gives us guidance on where quantum mechanics comes from. So one last step before we jump to quantum mechanics, and that's going from the Lagrange formulation to the Hamilton formulation. If the Lagrangian is typically t minus u, then the Hamiltonian is typically t plus u, but the real definition of the Hamiltonian is as the Legendre transform from the Lagrangian itself. Essentially, the Hamiltonian and the Lagrangian are two equivalent functions. They both contain all the information about the dynamics of the system. They're just different by a change of variables. And the key idea is that the Lagrangian is expressed in terms of coordinates and velocities, which is perfectly fine. But the thing that's really nice about the Hamiltonian is that the Hamiltonian formulates everything in terms of coordinates and momentum. So the Hamiltonian formulation takes this idea of a special relationship between P and Q, and it elevates it one step further. It now takes these to be the fundamental independent variables. And it uses those to express the dynamics. So if you do that, then instead of Lagrange's equations, you get one last version, the completely equivalent set called Hamilton's equations. Hamilton's equations of motion. And in terms of the Hamiltonian, those equations of motion are the derivative of the Hamiltonian with respect to momentum gives us the rate of change of the coordinates, and the derivative of the Lagrangian with respect to the coordinate gives us minus the rate of change of the momentum. So I have two sets of derivatives that I take on the Hamiltonian, and those two derivatives tell me the dynamics. They tell me the time dependence. So this describes the time evolution. Okay, great. Why is that useful? Why is this so nice? The thing that really helps us is that these equations are first order differential equations, whereas Lagrange's equations or Newton's equations are second order differential equations. Here we've changed everything up to make P and Q the central factors. And now I get two first order differential equations instead. And the really nice thing about this, which is what I'll show you next, is that that means that these dynamics can be expressed totally in terms of algebra. And that's the crux that makes it possible to go cleanly and unambiguously between classical and quantum mechanics. These are essentially algebraic in nature. So this is really, I think, where the story about quantum mechanics and then eventually quantum field theory comes from. The topic that I'm trying to summarize now is canonical quantization. I.e., where does quantum mechanics come from? Maybe let me pause here for a second before I go on. Any questions so far, or is everybody still with me?
I see mostly no.
Okay, good. I see thumbs up. Thank you. Okay, still sort of slow rolling the introduction. Now let's introduce a little more technical notation. It may not be obvious why this is so nice, but I am a real big fan of the Poisson bracket. What is the Poisson bracket? It's a funny combination of derivatives between P and Q. The definition of the Poisson bracket of any two quantities, A and B in classical mechanics, is a sum over all of the coordinates and momenta you have. And this object is a derivative of the first quantity with respect to a coordinate, derivative of the second quantity with respect to a momentum, minus the other way around. Derivative of the second quantity with respect to the coordinate, derivative of the first quantity with respect to the momentum. That's a strange looking object. Why would Poisson have ever come up with this thing? I can't tell you for sure, but the thing that's interesting about it is that it is anti-symmetric. Notice that it comes in with a minus. So a Poisson bracket is like a difference. It's some kind of measure of how do the quantities A and B depend differently on P compared to Q. Still kind of fuzzy. Why do I care about this and what does this tell me? The nice thing about the Poisson bracket is that it gives you a general coordinate independent way of expressing what it means for two objects to be canonically conjugate coordinates and momentum. So one nice feature of the Poisson bracket, if I have two coordinates, qi and qj, their Poisson bracket with each other is always 0. And the reason is just from this definition. If one of these is a q, the derivative of q with respect to p at constant q is 0. These are partial derivatives where I vary one independent variable while keeping the other one fixed. So if both quantities are q, then either this term goes to 0 or that term goes to 0, and I just get 0. For the same reason, if I take the Poisson bracket of two momenta, I also get 0, any two momenta. The one that's non-trivial is if I take one coordinate and one momentum, and only if they're exactly the right partners to match up, then I get something known as delta ij. So I get 1 if I have exactly the right coordinate and its partner for the momentum, 0 otherwise. So you can really regard the Poisson bracket as sort of the definition of what these canonical conjugate pairs are. So Poisson brackets are interesting. They express something about the relationship between P and Q. What else does it do? The Poisson brackets have an internal algebra all of their own. And that algebra, since those things are built from derivatives, it looks like the algebra of derivatives. Poisson brackets have their own algebra. So for instance, if I have the bracket of two quantities A and B, it's anti-symmetric by construction. So if I swap A and B, this thing changes minus sign. Another nice property is that if I have the bracket of three quantities, the bracket of A with the product B and C, the brackets follow a form of product rule. Just like derivatives do. In this case, because the Poisson bracket is defined from derivatives, that's how it's built. And you can show that that property leads to this form of product rule. So just like any other derivative, if I have an operation on the product B and C, the result is a sum of two terms, one of where I take the operation on C, the other one where I take the operation on B. So this is a product rule exactly like a regular derivative satisfies. They also have a very nice cyclic property known as the Jacobi identity. Whereas if I have a set of nested commutators, a set of nested Poisson brackets, A with B with C, plus all permutations. So I write B with C with A, plus C with A with B. The whole thing equals 0. So the point is not for you to memorize any particular one property of the Poisson brackets. Just recognize that they play by their own set of rules. They have their algebra all of their own. The other very interesting thing that comes from the Poisson bracket is using Hamilton's equations. So what happens if I put these two things together? My Poisson bracket definition was the bracket of A and B is sum over all pairs, derivative of A with respect to the coordinate, derivative of B with respect to the momentum, minus the other way around. What if I put this together with Hamilton's equations? The equations of motion tell me that if I take the derivative of the Hamiltonian with respect to Q, I'm going to get PI minus PI dot. And if I take the derivative of the Hamiltonian with respect to PI, I get QI dot. This object is going to happen anytime either A or B is the Hamiltonian. Then I'm going to get a derivative that looks exactly like this. So let me plug it in. What if I do have the Hamiltonian is one of the objects in that bracket? If I take, for instance, the Poisson bracket of a coordinate with the Hamiltonian. When I plug Q in for A, this first term gives me 1, and the second term gives me 0. So I just get derivative of the Hamiltonian with respect to P, and the derivative of the Hamiltonian with respect to P is Q dot. So it just so happens that if I take any coordinate and I take its bracket with the Hamiltonian, I get the derivative of that coordinate. In the same way, if I take a momentum, I take its bracket with the Hamiltonian. When I plug in P for A, the first term is 0. Now I get minus derivative of the Hamiltonian with respect to P. But the derivative of the Hamiltonian with respect to P is just no, I did this backwards. With respect to Q, that's better. So that gives me minus PI dot, minus of minus P dot. And so I get plus. So what does this tell me? It tells me if I take the bracket of a coordinate with the Hamiltonian, I get the derivative of the coordinate. If I take the bracket of the momentum with the Hamiltonian, I get the derivative of the momentum. The whole point of Hamilton's formulation is that P and Q are your independent variables. So if the bracket with the Hamiltonian tells me how Q changes, tells me how P changes, that's everything. That tells me how any function changes. And in fact, if I just plug this in now for an arbitrary function f that depends on P and Q, I see that the Hamiltonian gives its derivative also. So if I take any function f and I calculate its Poisson bracket with the Hamiltonian, then this is sum over all coordinates, derivative of f with respect to Q, derivative of the Hamiltonian with respect to P, minus derivative of the Hamiltonian with respect to Q, derivative of F with respect to P. If I just plug in Hamilton's equations of motion, the derivative of the Hamiltonian with respect to P is Q dot. dF, dQ, Q dot, and then minus derivative of the Hamiltonian with respect to Q is PI dot. So this is plus derivative of F with respect to P times P dot. This object is just chain rule, right? This is derivative of F with respect to Q times time derivative of Q, plus derivative of F with respect to P times time derivative of P. That's all possible time dependence of the function. So the right-hand side is dF dt. And this is given by the Poisson bracket of F with the Hamiltonian H. So something really remarkable has happened here in the definition of the Poisson bracket and what that does for the equations of motion. The Poisson bracket contains all of the information necessary to get the equations of motion. Once you have the bracket, you can forget about all of the original derivatives and things that gave rise to it. So there's something really special that tells me that the bracket of any function f with the Hamiltonian gives me the time derivative of f. So something about the Hamiltonian is responsible for, let me say, generating time element. And the thing that's so incredible about it is that it is entirely algebraic. So to illustrate what I mean, for example, if I have a Hamiltonian, which is the harmonic oscillator, e squared over 2m plus 1/2 kx squared. Right now I'm talking about classical mechanics, but the algebraic description here works equally well for classical and quantum mechanics. That's the point. So if I have a Hamiltonian and I calculate the Poisson bracket of it, if I want to know what is the rate of change of the momentum in this Hamiltonian, I can get it completely just from the bracket of P with the Hamiltonian. And that follows completely just from algebraic properties. What's more my potential? It's 1/2 kx. So if I just have the known bracket properties, I know that the bracket of P with itself is 0. So this term goes away. If I have that, then just on the basis of the bracket properties alone, I just need to calculate the bracket of P with 1/2 kx squared. But this bracket acts like a derivative. It satisfies product rule, and so it also satisfies power rule. When I use that product rule property, I get a single factor of kx out front times the bracket of P with x. And the bracket of P with x is -1. So just on the basis of algebra, I could have completely forgotten about all of my original derivatives and the classical mechanics that generate. Just on the basis of algebra, I get P dot is the bracket of P with the Hamiltonian, and that's equal to -kx. In the same way, if I have x dot as the bracket of x with the Hamiltonian, that's the bracket of x with P squared over 2m plus 1/2 kx squared. Again, for the same reason, the bracket of x with itself is 0. So the only thing I keep is the bracket of x with P squared over 2m. Because it satisfies power rule, essentially, I can pull out a factor of 2 and a factor of P, and then I have the bracket of x with P. And this bracket is just 1. So all of the equations of motion, all of the physics you need to solve the system can be obtained just from these weird algebraic brackets. Not only that, the solution to the equations of motion can be written in terms of the action of these brackets. So if I have so we said that for any function f, the bracket with the Hamiltonian gives you df dt. If I can get one derivative of f like this, if I do it twice, I can get 2 derivatives. And if I do it again, I can get 3 derivatives. If I'm willing to keep forming nested commutators, I can make any number of derivatives. Sorry, not commutators, Poisson brackets. Maybe another way that one can write this is to think of it as an operator that acts on the function f. So let me rewrite this same notation a little bit differently. I want to consider this bracket as an operator. So I'm going to use this fill in the blank notation. This is supposed to mean the bracket of f with h. And when I write down a bracket with a fill in the blank, that means this is an operator that's acting on whatever comes next, and whatever comes next gets filled into that blank. So in that notation, I can write this same expression to say that to get the time derivative of something, all I have to do is fill in the blank of whatever I want it to act on with the Poisson bracket with the Hamilton. So I'm going to take this and run with it. If I have any smooth function of time, I can write that smooth function in terms of its Taylor series. This is f of 0 plus t times df dt plus 1/2 t squared times the second derivative plus ... If I write this whole thing as derivatives acting on the function, then this is the identity operator plus t times the first derivative plus 1/2 t squared times the second derivative, and so on, all acting on the function f, and I only care about it at t equals 0 at the end. The point is that all of these terms can be represented by a Poisson bracket. So I can write this as 1 plus t times fill in the blank with the Poisson bracket with the Hamilton. The next term is 1/2 t squared and a double Poisson bracket. Fill in the blank of the Poisson bracket. Yes, Poisson bracket of the function with the Hamiltonian, and then take another Poisson bracket of that with the Hamiltonian. Let's start. I'm trying to show that not only the differential equation can be written in terms of the bracket, but the whole solution can be written in terms of the bracket too. This object, 1 plus something plus 1/2 something squared plus ... This is a series that I know how to sum. What is the summation of that infinite series? Anybody? Say again, it's the exponential, exactly. So it might be a bit of a formal notation, but I can completely write the infinite action of multiple of these Poisson brackets as the exponential of t times the Poisson bracket with this fill in the blank notation. All of it acting on the function f of t at t equals 0. So in essence, if I know how the bracket works, I know everything. I know the equations of motion, I know the solutions to the equations. What on earth does that have to do with quantum mechanics, much less quantum field theory? I argue that this condition, the fact that I can write down all of classical mechanics just using algebra, puts a very strong constraint on what kind of quantum mechanics I can have. The reason is that whatever quantum mechanics is, it has to match on to classical mechanics somewhere. There has to be a correspondence principle. In quantum mechanics, that correspondence principle comes in the form of Ehrenfest's theorem. So Ehrenfest's theorem talks about averages. It says that if I take the rate of change of the position on average, this has to look like classical mechanics. I get the average momentum divided by. Similarly, if I take the rate of change of the momentum, I need to get negative derivative of the potential. The key here for Ehrenfest's theorem, the connection between classical and quantum mechanics, is these average values. So the point is that quantum mechanics can fluctuate, There are quantum fluctuations that are generated by the uncertainty principle, but on average, classical and quantum mechanics have to look the same. They have to look the same. That is non-negotiable. So quantum mechanics has quantum fluctuations. And those are due to the uncertainty principle. But on average, quantum mechanics has to map back to classical. And the point that I want to make is that we have just shown exhaustively that classical mechanics is totally described by the action of a bracket. And I'm going to argue that that means that quantum mechanics must also be controlled by a bracket. Not just any object, but something that has exactly the same algebraic properties as the Poisson bracket. So the point is, in classical mechanics, using Hamilton's formulation, that time derivative of the average of x is the same thing as the average of the Poisson bracket of x with the Hamiltonian. And likewise, the time derivative of the momentum, that's also given by the average of the bracket of the momentum with the Hamiltonian. So if I don't know anything about quantum mechanics, if I've got to invent it for myself for the first time, how do I do it? I do it by recognizing the structure of classical mechanics in terms of these brackets. And I try to pick a picture of the quantum mechanics called the Heisenberg picture. In the Heisenberg picture of quantum mechanics, that average doesn't do anything important. In the Heisenberg picture, the states are not time dependent. In the Heisenberg picture, then basically I can pull all the derivatives inside the brackets. I pull the brackets outside completely. So I can construct quantum mechanics for the first time if I can find a bracket such that in the quantum theory, ddt of my x, whatever that's supposed to mean, equals some kind of bracket of x with the Hamiltonian. And ddt of the momentum needs to be some kind of bracket of the momentum with the Hamiltonian. So the question of how do I quantize my classical theory all boils down at the end of the day to what is the correct bracket and how do I use it? That answer is pretty much unique. So if my quantum theory is a theory of linear algebra, if it's a theory of state vectors, psi, that live in a Hilbert space, a complex vector space, complex Hilbert space, then the language of quantum mechanics is supposed to be vectors. The actions one takes on vectors are linear operators. So as soon as I decide what the language of quantum mechanics is going to be, that it's going to be linear algebra and vectors, I know that the relevant bracket that I need is the bracket of linear operators. That is the commutator. So the quantum bracket is the commutator. And the point is that I can take my classical mechanics in terms of the Poisson bracket of any two functions A and B, and I can turn this into the corresponding quantum expression unambiguously by replacing that Poisson bracket with minus I over h bar times the commutator of A and B. This prescription that tells you how to take something in classical mechanics and turn it into something in quantum mechanics just by matching the brackets is known as canonical quantization. So this is really the foundation of where field theory is going to come. Yes, please, question.
Sorry. Yeah. Is there any obvious reason why we consider complex Hilbert spaces when considering quantum mechanics. Like,
Yes, I think the reason is that quantum mechanics has to work at the amplitude level, which means that you can't make quantum mechanics if you assume that the probability is the underlying wave mechanic. You need probability amplitudes, and then the probabilities are the absolute square of that. So I would say it's sort of experimental fact that like a Stern-Gerlach experiment, other things like diffraction patterns, those tell us that quantum mechanics is wave mechanics, that it works at the amplitude level. And that means that my amplitude should in general be complex, something that I square to get a probability, but that I can still have waves in. I need some complex phase rotation. Well, we'll get to that in a minute with the Schrodinger equation. But essentially, the Schrodinger equation just tells you that if you have a stationary state, the probability density doesn't change, but the real and imaginary parts of your wave function slosh back and forth. So it's a rotation of the complex phase. If you don't have that, I don't think you have quantum mechanics. I don't think you have any of the underlying wave mechanics that you need. So I think the answer is you need a complex vector space in order to have non-trivial probability amplitudes. Does that make sense?
Yeah, sure. I'll take it. Thank you very much.
Sure. Yeah, good question. Okay, so I'm trying to build the foundation of how do we quantize a classical theory, because this prescription is what's still going to work for us when we go to quantum field theory and no longer the quantum mechanics of a few particles. Okay, the comment that I was making about the Schrodinger equation is that it comes from somewhere. The Schrodinger equation follows from this prescription for canonical quantization. So in particular, we saw that any function f of t, I was able to write as a formal exponentiation of that Poisson bracket, t times the bracket of fill in the blank with the Hamiltonian, acting on my function f of t. If I quantize this, I just replace the bracket by the commutator. Then now in a quantum theory, I would say some observable, let me call it omega as a function of t. The time dependence of an operator in the Heisenberg picture of quantum mechanics should be written as e to the minus I over h bar commutator of this thing with the Hamiltonian, acting on omega of 0. It turns out if you expand that exponential and regroup the terms, this expression in terms of a commutator is exactly equal to e to the plus I over h bar Hamiltonian times omega of 0 times e to the minus I over h bar Hamiltonian times. It's a really funny thing where in the classical picture, this is about as far as you can go. You write it as some formal expression. But once I make it a commutator, I can actually unscramble the factors. And that gives me the time dependence in terms of a unitary time evolution operator.
Yeah.
Matt,
Yes, sir.
you missed the T in your time evolution operator.
Did I? Where did I drop it? Oh, T. Thank you. Yes. So the point is, canonical quantization just gives you for free. It comes right out of it. What is the time evolution operator? It gives it to you in terms of this exponentiation of the Hamiltonian. So the time evolution operator in quantum mechanics is e to the minus I over h bar Hamiltonian times time. Where does that come from? It's not an accident, the minus I over h bar. It's this minus I over h bar. It came because the Hamiltonian always generates time evolution. It generates time evolution classically. It still generates time evolution quantum mechanically. But when I switch from a classical representation to a quantum or unitary representation, the physics is the same, but the picture changes. So the same solution can be written in terms of that time evolution operator. That time evolution operator is the time-dependent Schrodinger equation. So my state psi at some time t is given by that time evolution operator. E to the minus I over h bar Hamiltonian times time acting on the state psi of 0. This equation, if I just take the derivative of it, IHR ddt of psi, is precisely the Hamiltonian acting on psi. This is the time-dependent Schrodinger. So I'm not trying to tell you that I just derived the Schrodinger equation out of nothing. No, you don't get it for free. The Schrodinger equation is totally equivalent to canonical quantization, but canonical quantization is more general. It helps you understand not only how you turn the Hamiltonian responsible for evolving in time into a unitary object. It does the same thing for translations, for rotations, for any classical canonical symmetry transformation. You can do exactly the same thing, and it will always transform to the corresponding unitary operator that's. So I'm trying to argue here that essentially algebra dictates the structure of quantum mechanics. There are not infinite possibilities for what quantum mechanics could be. Only things that match on to the bracket structure of classical mechanics will ever have a correspondence principle. Okay, that gets us from F equals ma to quantum mechanics. What do we do after quantum mechanics? The limits of quantum mechanics come when we try to put quantum mechanics together with relativity. So let's say wave mechanics, which is the quantum mechanics of a fixed number of particles. Wave mechanics fails spectacularly when combined with relativity. And really here I just mean special relativity. Gravity is too hard for me. Why do I say that fixed particle number quantum mechanics fails spectacularly when you try and combine it with relativity? There are several fundamental flaws that show up as soon as you start allowing relativity and quantum mechanics to talk to each other. The first and perhaps hardest to avoid is the necessity of a multi-particle theory. Necessity of multi-particle theory.
Sorry.
Yes.
Why is it fixed number of particles specifically? Like, why does the particle number have to be fixed for wave mechanics?
Yeah, so the fixed number is something that's an intrinsic part of so-called first quantization, the traditional way of doing quantum mechanics. Usually you talk about an electron which has a wave function. Or if you have a 2-electron problem, you have a wave function for 2 particles that depends on 2 variables. But what you don't have is dynamics that are capable of changing the number of particles. Traditional quantum mechanics can't handle that. You can't start with 1 electron and then go to 1 electron plus a photon, or even worse, 1 electron plus a muon anti-muon pair. Those sort of fluctuations that can create particle-antiparticle pairs are not something that traditional quantum mechanics can handle, sort of because you're changing the meaning of the wave function. You would need to be able to sort of on the fly change from a 1 particle to a 2 particle to an n particle wave function. Does that answer the question?
Thank you.
Sure. So this is the critical difference between so-called first quantization, or the wave function picture of quantum mechanics, which always has sort of built in the idea of a fixed number of particles, versus what will become quantum field theory, where you have to build in from the beginning the fact that I can have interactions that will change the number of particles in my system. So, right, I'm claiming that a multi-particle theory is an inevitable consequence of combining together the uncertainty principle, which tells me energy is not fixed. Energy can fluctuate, but only for a short amount of time. The Heisenberg uncertainty principle tells me I can borrow as much energy as I want. I can randomly fluctuate up or down, but the more energy I borrow, the bigger the fluctuation, the shorter the time it lives. So if I have a small fluctuation, it's long-lived. If I have a big energy fluctuation, it's short-lived. That's all fine and good in single particle quantum mechanics. The problem is when you put it together with relativity. Relativity takes the uncertainty principle and adds to it the ability to create particles through E equals mc squared. So the combination of these two things means that in a relativistic quantum theory, I may have a quantum fluctuation that randomly generates a bunch of energy for a short period of time, and that energy can be used to create new particles. So in a relativistic quantum field theory, it happens all the time that something that starts off as a single electron actually fluctuates and turns into a single electron plus a photon. And not only that, I can fluctuate the electron and then I can fluctuate the photon into a particle-antiparticle pair. And those can be anything. They could be muons, they could be quarks, they could be undiscovered supersymmetry particles that we would love to find someday. But anything that can happen does happen in quantum mechanics. And that is sort of an inevitable consequence of letting these two guys talk to each other, Heisenberg and Einstein. So when we construct a quantum field theory, this is something that needs to be baked in from the beginning. I cannot have a quantum field theory that only limits me to the one particle sector. I need to be able to dynamically move from 1 to 2 to 3 to any number of particles as my interactions tell me. So that's sort of the first insurmountable problem of relativistic wave mechanics. You have to have a multi-particle theory. Second insurmountable problem is negative energy solutions, also called antimatter. So second insurmountable problem is that the relativistic dispersion relation sometimes you see this called the Einstein relation. That is E squared equals PC squared plus MC squared squared. I'm much more used to calling this relation the on-shell condition. So if you hear me refer to it that way, that's why. Why is this an on-shell condition? Because if I subtract this thing around, this looks like E squared minus P squared equals M squared. And this describes a four-dimensional surface. If this minus were a plus, it would be a hypersphere in 4 dimensions. The minus means that it's a hypersphere in non-Euclidean geometries, a Minkowski sphere, so to speak. So this is like saying I have a spherical shell with particular radius. That's why this is the on-mass shell. The problem that arises from this is that if I put this piece of information into my wave mechanics, I always get two solutions. I always get plus or minus the square root of E squared plus M squared. And here I'm already setting C equals H bar equals 1. I'm rapidly going to forget my units in just a bit. So the problem is that there are negative energy solutions. And that's not just an accident, right? That's it's a generic feature of the relativistic equation. There's various ways to try to deal with this. Dirac famously introduced the idea of the Dirac sea, that you could have negative energy states, but they're all full. They're all full of electrons. And that gets right the idea of antimatter, that I can take out one of those negative energy solutions, and subtracting a negative energy particle looks an awful lot like adding another positive energy. But the Dirac sea doesn't work if you take it literally. For one thing, it only applies to fermions. It doesn't help you at all if bosons exist, and they do. The other thing is that if you take the Dirac sea literally, it means that there's an infinite amount of charge just sitting around in the vacuum, that the vacuum has an enormous amount of charge, and that should lead to some physical consequences. So the literal interpretation that Dirac tried to advocate to get around these negative energy problems sort of slightly worked in his case, but it's not really a foundation for a general. It doesn't help you at all if you And then the last, maybe the most challenging problem to resolve is failure to reconcile causality. Causality in quantum mechanics. Causality means that two measurements should not be able to affect each other if they're separated by more than the speed of light. And you can quickly check using that time evolution operator. In just ordinary, say, non-relativistic quantum mechanics, if I start off at an initial position R0 and I evolve with time to some final position R, this object is a measure of my propagation amplitude. Let me call it the propagator. I'm going to call this, please forgive the abuse of notation, U of R minus R naught NT. This object is well defined. The time evolution operator is e to the minus I over h bar Hamiltonian times time. Suppose I'm just dealing with a free
Sorry, I have
particle.
a question.
Question?
Yeah. This is got to do with the negative energy solutions that you were talking about.
Yes.
You mentioned something to do with fermions, and then you briefly mentioned bosons.
Yes.
But I don't
sorry.
think I don't think I've ever come across a concept of a bosonic antiparticle. So
Right. Very good. So maybe let me elaborate a little bit. Usually when people are first introduced to the idea of antimatter from the Dirac equation, it's in the context of the Dirac C. So you'll say, I have E equals P squared plus M squared square root. Basically, I'm going to get a dispersion relation where, let's see, so this is energy as a function of P. I have some minimum value for the mass, and then the energy increases, I guess, like a square root. Something like this. And then I have negative energy solutions that look something like this. If I were doing non-relativistically, I would say energy is P squared over 2M, maybe plus MC squared. So usually the picture that you see looks something like this, and people are talking about electrons, where the idea is that if this is Dirac C, zero energy is here, then all of these negative energy states are actually full. Just starting off, in an empty universe, if the energy is zero, then anything with less than that is full. And Dirac's picture of antimatter was that if I take a particle down here, one of these filled energy levels, and I add energy to it, I can promote the electron up to the positive energy solution. And I see an actual electron here, and the counterpart would be a hole, which looks exactly like the electron, but it has the opposite charge. And so this was sort of the argument for the positron being effectively like a hole, an anti-electron, an absence of a negative energy electron in the Dirac C. This gets right the idea of antimatter. It gets right the idea of pair production. That if I have a photon with enough energy equal to 2 MC squared, then I can create a particle-antiparticle pair. One of the problems with this is that this whole idea only works if you have antimatter fermions. So the problem, for instance, is that antimatter bosons exist. So for example, if I tried to draw exactly the same thing, but instead of talking about electrons, I'm talking about pions, pi plus and pi minus. Pi plus and pi minus are bosons. They're scalars. They're spin zero particles, but yet they have an electric charge. The pi plus and the pi minus are antiparticles of each other. So I could still draw the same kind of Dirac band structure for the pions, but it doesn't make sense anymore. If these are pions, then there's no Pauli exclusion principle. If that's the case, then I can just fill up any infinite number of pions and they would all just fall down into the negative energy C. Dirac's whole picture relied on the idea of Pauli exclusion to sort of fill up the levels and then leave you here where everything below zero is full, everything above zero is empty. So the point is that gets some things right, but you can't take it literally. That's not an adequate solution for everything. For one thing, it doesn't help you at all if you have antimatter bosons. For another thing, if this was literally true, and I have an infinite number of electrons sitting down here in the negative energy, then that means that my charge of the vacuum is negative infinity. I have all of this charged stuff filling up the empty vacuum. So there are multiple ways to see why Dirac's C hole interpretation doesn't really get you that far. But I think maybe this is the easiest one to understand, that it just only applies for fermions. And if there's even one antimatter boson in nature, then this whole theory would collapse. Does that answer the question?
Sure. I suppose when you said bosons, I was thinking more about the force carriers, like a photon,
Sure.
for example.
If it helps, one could make the same argument about the weak bosons, say W plus and W minus. Those are vectors, also antimatter vectors from each other.
Okay. Thank
Yeah,
you.
okay, great. Right, so the last, maybe most difficult problem to solve is the problem of causality. And right, we were setting up this propagator expression, and we can actually evaluate this using the technology that we've already put together. So if my propagator over a displacement r minus r naught n times t is equal to the bra position r, e to the minus I over h bar e squared over 2n times time naught. I know how to evaluate the momentum operator on position states. The easy way to do it is by Fourier transform. So I just insert a complete set of states, integrate over all momenta, and I put in the momentum states P. Of course, the momentum states are eigenstates of the momentum operator. So when the momentum operator hits that state, I just get the number e to the minus I over h bar p squared over 2nt out of it. This object is just the plane wave. This is 1 over 2 pi to the 3 halves e to the plus I h bar, I think, e dot r. So if I got all my factors right, then when I plug everything in, I get integral d3p over 2 pi cubed e to the I over h bar e dot r minus r naught times the Gaussian e to minus I over h bar e squared over 2nt. If I got my phases right. Yes, I think so. Yeah, probably in my notes I set h bar to 1. And this is just a Gaussian integral, right? This is a Fourier transform of a Gaussian. The Fourier transform of a Gaussian is also a Gaussian. So you can do the integral, you can do it by hand, or you can plug it into Mathematica. And what you get is this. The answer is some amplitude that decays with time. And then the answer is Gaussian with an imaginary argument. Okay, the specific details of the answer aren't super important. What is important is that this answer remains non-zero, even if the 2 points are separated farther than the speed of light can connect. Even if r minus r naught is greater than c delta t. So this is a violation of causality. It means that the fact that the quantum wave function extends out over all space tends to allow communication faster than the speed of light, unless you do something. If I take any version of my quantum mechanics, single particle quantum mechanics, it's going to suffer from this problem. The tails of that wave function will be able to send information faster than the speed of light. Here we've plugged in just the non-relativistic kinetic energy, but if you change that to the relativistic kinetic energy, it doesn't fix anything. No small changes to the kinematics can fix this. This is a fundamental problem that quantum field theory only solves in a very elegant way by canceling the contributions from particles and antiparticles. So even in a quantum field theory, this still remains true. Even in a QFT, the amplitude for a particle to propagate propagate outside of the light cone is non-zero. So quantum field theory can't fix that problem. The amplitude for a particle to propagate still goes outside the light cone. What quantum field theory solves, however, how it restores causality, is that you get a cancellation between a particle going from point A to point B and an antiparticle going backwards from point B to point A. Quantum field theory solves this problem by canceling particles and antiparticles. How does that work? If I have a space-time diagram where time is on the y-axis and space is on the x-axis, if I have 2 points that are causally connected, so if this is my forward light cone, so this is x equals ct, x equals minus ct. Anything that is within the causal past or the causal future is sitting inside these light cones. So the point is, in a quantum field theory, if my 2 points are causally connected, if the origin can actually have an influence on here, then there's an imbalance. I have more particles coming into the future than antiparticles coming back. But if I've got a point which is outside the light cone, something that would require me to go faster than the speed of light to affect it, the way quantum field theory solves this problem is that you have exactly the cancellation of a particle going from point A to point B, with an antiparticle coming back from point B to point A. So the point is, the solution is different. The solution is not that I find a way to force this thing to go to zero. It's that I cancel something between the particles and the antiparticles, which are necessary in quantum field. All of this is to say that first quantization is dead. There is no way to salvage wave functions and fixed particle number quantum mechanics in a relativistic theory. If you want to do the relativistic quantum mechanics that's necessary to get QCD, you have to be working in a quantum field. So that is the end of my first spiel about why quantum field theory, why is it necessary, what does it do?
We have a question.
Yes, please.
So I wanted to ask about the whole particle antiparticle cancellation you just mentioned. How
Yes.
does that discriminate between the inside and the outside of the light cone?
The way that it discriminates between inside and outside the light cone is based on the transformation properties of special relativity. So for instance, there's a significant difference between two events or 2 points in space-time that are causally connected versus ones that are causally disconnected. So part of the beauty of special relativity is that if I have any 2 points that are inside the light cone, if they're able to communicate with each other, I can always choose a frame of reference such that they're sitting at exactly the same position and they move only in time. So if something is inside the light cone, I can always make it look like it's moving only along time and not along space. The same thing is true if I have something that's space-like separated. If I've got 2 points that are outside the light, I can always go to a frame where they are happening at the same moment in time, but at 2 different points in space. So I can always go to a frame where the event separation looks like this. That is the fundamental difference. So the way that the proof goes is basically based on saying, my answer doesn't depend on my frame of reference. So I'm allowed to boost it and change it however I want. If I start with 2 events that are in the future causal light cone, then I go to a frame of reference where they're sitting at the same point and I look at it. If I have 2 points that are sitting at the same time in different space points, then they're on an equal footing. The cancellation essentially comes because there's no longer any difference between going from X to Y and going from Y to X. I can sort of rotate the entire problem around. Once everything is sitting at exactly the same time slice, then I can rotate the problem and turn X going to Y into Y going to X. cannot do that here, because here the separation is time. Here a rotation doesn't change anything, but here the rotation lets me turn the problem into the inverse problem. The cancellation. Does that help?
Okay, thank you. Yes, that's.
This is discussed very nicely, by the way, at the beginning of the textbook Peskin intro.
Sorry, what about like separations?
Oh, very good. Like separations, you can similarly treat like separations. So if you have like separations that are precisely along the light cone, things that are like separated in one frame are like separated in all frames. I think the statement is that you must have a massless particle in order for a signal to propagate along the light cone itself. So I would say you can get this, you can get this, you can get this only if m is equal to 0. Otherwise, if the particle has finite mass, then it can't go all the way to the speed of light. Does that answer the question? I feel like I maybe misunderstood the purpose of the question.
Yeah, I mean, sure, that's fair enough. Thank you.
Yeah, maybe let's think about it some more and come back to it if I haven't fully answered your question. Okay, so this is what's supposed to bring us to quantum field theories. And quantum field theories come in many varieties, of course. Let me switch and share my screen for 1 second. I have a figure I want to show. Are you guys seeing my screen?
Yes.
Looks good. Yes.
Very good. So the idea that I had in my mind for this initial lecture is sort of the map when you're at the mall, the big "you are here" that helps you locate where you are in relation to all of the other pieces. This is the "here you are" arrow in terms of where QCD lies among quantum field theories. So the next thing that I want to discuss is, what does this landscape of quantum field theories look like? There are a number of free quantum field theories that effectively define what the kinds of particles in nature can be. We'll talk about those. The really interesting part is when you try to solve interacting theories that you usually can't solve exactly. That's when you have to bring in all this fun technology of perturbation theory to try and solve them. There are perfectly good interacting theories that do not require gauge bosons. So phi cube theory, phi fourth theory, Yukawa theory are all perfectly good theories of nature that we can solve and describe that just happen to not have any photons in them. They don't have any gluons. But for theories that do have vector bosons in them, especially massless vector bosons, those theories are special. Those theories are called gauge theories, and they deal with symmetry in a very unique way that's related to how they allow the photon or the gluon to exist in the first place. So among interacting theories, gauge theories are special. Gauge theories are theories that contain massless vector bosons. And of those gauge theories, one of them is quantum electrodynamics. That is the gold standard for any quantum theory you would like to invent. And the theory that we care about is QCD, which is highly, highly analogous to QED, but with a different gauge group, the non-abelian gauge group SU3. So that's what I want to talk about next. We'll see how far we get in the time that I have now. But I want to set up the discussion of what is a gauge theory, what makes a gauge theory special, and what happens when we try to take that gauge theory from U1 electrodynamics to a non-abelian SU3, which gives us QCD. Okay, so first a few words about quantum field theory in general, just for completeness. The quantum field theory is a beautiful way of generalizing Lagrangian dynamics to infinite numbers of degrees of freedom, to infinite degrees of freedom. So whereas before, when we talked about the action that then gets minimized when we integrate over time with the Lagrangian, now we're going to talk about integrating something not only over time, but also over space depends on t and x. And it just so happens that if I'm integrating my Lagrange density, technically it's a different thing than the thing we called the Lagrangian before, but usually we don't bother to distinguish them and we just call it the Lagrangian anyway. In terms of this Lagrange density, where I'm integrating over all space and time, that's conveniently expressed as a four-dimensional integral over all space-time of the Lagrange density that depends on the space-time point x mu. That's one nice advantage of working in this Lagrangian formulation, is that's nice for relativity because it treats space and time equal. That makes it better for us than the Hamiltonian formalism, which was good for non-relativistic quantum mechanics. In non-relativistic quantum mechanics, you don't need space and time on an equal footing. So the Hamiltonian works perfectly well. But it's not well suited for a relativistic theory because that sort of biases you in favor of time in a way that's different from how space is treated. So what does a Lagrange density for a quantum field theory look like? The simplest Lagrange density is the free scalar theory. Free scalar Lagrangian. If I have Lagrangian is 1/2 d mu phi minus 1/2 m squared phi squared. This describes, although it may not be obvious, this describes the physics of an elastic medium distributed through space. Here, phi of x and t is the field. And this field is sort of reminiscent of the old idea of the luminiferous ether. The idea that there's some medium filling up all of space that's responsible for allowing certain wave modes to propagate back and forth. That's exactly what this does. Phi is that ether, phi is that field. It's not literally the same ether, but it's spread over space and time in exactly the same way. What happens to that? Notice here that I have the repeated index mu, repeated Lorentz index mu. This notation, if you're not familiar with it, stands for the difference between the time derivatives and the space derivatives. So this repeated index mu is summed from 0, 1, 2, and 3. 0 is the time-like index. 1, 2, and 3 are the space-like indices. And because we're not working in Euclidean space, we're working in Minkowski space, we have that funny minus sign that appears between time and space. What does that mean? That means that this Lagrangian, even though it's for a free particle, often we call this just the quote-unquote kinetic. Even though we usually call it just the kinetic term, it's not just kinetic energy. And you can see that if I expand this, my Lagrangian is 1/2 phi dot squared, the time derivative, minus 1/2 gradient of phi squared, minus 1/2 m squared phi squared. So this is a rewriting of the free Lagrangian. Notice that it contains the kinetic energy. If I think of this as my Lagrangian is t minus u, then t is this. This is the actual time-dependent part, the part that comes from the kinetic energy of a wave on that elastic medium oscillating up and down. That's the oscillating up and down at a single point that contributes to the kinetic energy of that point. So if this is properly the kinetic energy T, this piece is something else. This piece comes from gradients of phi. This is like a shear or the elastic energy of deforming that field. So this is the spring-like part. This is the part that comes from stretching or compressing that medium, that field phi that extends over all space. So this piece is the elastic energy of the field. Usually we call these two things together part of the kinetic energy or the kinetic term, because both of those things are necessary to give me wave behavior. The combination of acceleration of the field up and down at a point, and shearing of the field in space is what gives you simple harmonic motion. So I need both of those things to give me wave solutions that actually propagate momentum through space. If this is like a spring, then what's the spring constant? In these units, the spring constant is 1. That's there because I need the speed of that wave to travel at the speed of light or less. If that spring constant is 1, then that makes the speed of the wave 1, the speed of light. And if I have this extra mass term, then that's extra damping. That slows down the wave a little bit to give you less than the speed of light if you have something propagating with a finite mass. So what do I do with that action? I do the same thing that I did before. I minimize the action. So if I have action is integral d4x times L, where L is this Lagrangian, then I find the equations of motion by setting the derivative of the action equal to 0. And when I do, I get the Euler-Lagrange equations back, but in a more generalized form. Compare the old version of the Euler-Lagrange equations for a fixed number of particles, or a fixed number of degrees of freedom. That was ddt, derivative of the Lagrangian with respect to q dot, minus derivative of the Lagrangian with respect to q is equal to 0. The field theory version comes from the same place, but now it includes both space and time on an equal footing. The new equation of motion is derivative of any of the components, time or space. And then now I have a generalized momentum, variation of the Lagrangian with respect to any of the gradients, could be space gradient or time derivative, minus variation of the Lagrangian with respect to phi is equal to 0. So again, very similar equations, just now generalized to space. If I apply these equations to this Lagrangian, then the equation of motion that I get for my free scalar field is d mu plus m squared phi is equal to 0. Sometimes written box plus m squared phi equal to 0. What is this equation called? Very famous equation in relativistic wave mechanics.
Now the Klein-Gordon equation.
The Klein-Gordon equation. Very good. The Klein-Gordon equation is the mandatory starting point for any relativistic wave theory. This equation is minimum for any other particle. A scalar field theory only has the Klein-Gordon equation, but any other relativistic theory, the Dirac theory, the vector theory, all of those particles also solve the Klein-Gordon equation, but they have something extra. They also have internal degrees of freedom associated with this. The solutions to the Klein-Gordon equation can be obtained straightforwardly by Fourier transform. The general solution is straightforward to construct. So the general solution for your free field phi of x is written as an integral over momentum modes, integral d3k over 2 pi cubed 2ek. I have an arbitrary coefficient a sub k e to the minus I k dot x plus a k dagger e to the plus I k dot x. Yes. So this general solution comes from performing a Fourier transform on this Klein-Gordon equation. When you perform that Fourier transform, you get a constraint equation that tells you p squared minus m squared equals 0, or p squared equals m squared. This object was just the Einstein relation that we mentioned before. The 4 vector p squared is equal to the energy squared minus the momentum squared. So this is the on-shell condition now coming as an output from the Klein-Gordon equation. So for any momentum mode that is on shell that satisfies p squared equal to m squared, both waves, the positive energy wave positive energy and negative energy are both valid solutions. So all you need is this form for the general solution together with any momentum satisfying this on-shell constraint that gives you all possible solutions to the free Klein-Gordon. That is a classical field theory. How do I get quantum theory out of it? The same way that I did before. I do it by canonical quantization. So how to get a quantum field theory? Same answer as before, canonical quantization. The difference is that now I have an infinite number of degrees of freedom, whereas before I had my Q's and my momentum P was given by the derivative of the Lagrangian with respect to Q dot. Now, I have a different free variable for all possible points of the field in space. Right, so this means I have infinity degrees of freedom for each point in space. I have 1 degree of freedom for every point of space. But for each of these variables, I can define a conjugate momentum in exactly the same way. It's just the generalized version of this. So the canonical momentum to the field, canonical field momentum, is often written pi of x. And this is defined as the variational derivative of the Lagrangian density with respect to the derivative phi dot. So totally analogous to the derivative of the Lagrangian with respect to Q dot, except now I have any possible phi of x as my variable. If I can define canonical variables and canonical momenta, then I can impose canonical quantization. That means I'm not even going to bother with Poisson brackets anymore. I can just go straight to imposing the commutators that will be necessary to make them. So the canonical commutation relations tell me that any two of the variables commute with each other at equal time t. Any two of the momenta, pi of x and t, pi of y and t, they all commute with each other. The only thing that does not commute with each other is 1 phi and 1 pi. They give I h bar, but I put h bar equal to 1, so I just get I, and I only get I if I have the same x and the same y. So in this 3-dimensional notation, I should get a delta function of x minus y. So these are our canonical commutation relations for the fields. Canonical commutation of fields. It's the same procedure as before, but now just using more variables. This is really just the input. It's not very interesting on its own. What's really interesting is the output. If I take this as the input and I plug in the free field solution for phi and pi, what I find are constraints on A and A dagger. What this tells me is that A and A dagger work like creation and annihilation operators. Two of the A's commute with each other. Two of the A daggers commute with each other. But 1A and 1A dagger do not commute with each other if they're the same momentum mode. So the output of these commutation relations on the field is these commutation relations among A and A dagger. And that implies that A and A dagger act as annihilation or creation operators. And what do? They create single momentum modes or excitations of the field. So this is the conceptual change from first quantization. In first quantization, there was always one particle and you were trying to find its wave function. In second quantization, you may have any number of particles. By allowing a dagger to act once on the vacuum, you create a single excitation, a single plane wave mode of that field. And that plane wave mode is the particle. That is an object that has definite mass, definite momentum, definite energy, definite spin. It is a particle with a well-defined plane wave mode. But nothing stops you from creating as many of those single particle modes as you want. You can create a quantum field theory state that is made up of a billion particles with different momentum. You could make a coherent state made up of infinite numbers of particles. Quantum field theory allows you to do all of that. Anything that you can do by raising and lowering the harmonic oscillator with A and A dagger, you can do to a quantum field theory to create or destroy a plane wave excitation of the field. And that's what we mean by quantum. So that is what second quantization is. Got about 15 minutes left to wrap up the discussion. Other questions so far? Okay, then let's continue. I'm sorry, question?
Yep, looks good. Just
Okay, then let's continue with the classification of field theories. So as I was arguing, free field theories. What do I mean by free field theories? I mean that their equations of motion are linear. That means that they satisfy the property of linear superposition. And that means I can add two solutions without them interacting with each other. So a free field theory is one that has a superposition principle, and that means its equations of motion are linear. That means their Lagrangians are at most quadratic in the field. That's why my Lagrangian in terms of the scalar theory, d mu phi minus 1/2 m squared phi squared. Notice that this thing depends quadratically on phi. I've got two derivatives of phi paired up to make something which is Lorentz scalar. And then I've just got phi squared. Notice, by the way, that the Lagrangian must be Lorentz invariant. Must be frame independent. Frame independent in special relativity is easy. It just means that it must be a scalar when you build it out of four vectors. Lorentz transformations can just be thought of as rotations, quote unquote, of those four-dimensional vectors. So if I have something that is a scalar built out of the four-dimensional vectors, then it does not transform when you rotate. So hence, if this is the vector d mu phi, its square is Lorentz invariant. There's one mu downstairs, one mu upstairs, and they're all paired. Similarly, phi squared is Lorentz scalar. So really, I can write down a Lagrangian, which is a free theory for anything which respects special relativity. And that's a very powerful statement. And write down a free Lagrangian for any particle, or maybe any field would be a better way to say it, which respects relativity. That's very powerful because it is possible to write down the algebra of the symmetry translations of special relativity. Special relativity is written as the symmetry group SO plus 3, 1. This basically just means that I have rotations in 3 dimensions. I have boosts in 3 dimensions. And time is special. So it's not just rotations in 4 dimensions, that would be Euclidean space. The fact that I have Minkowski space means that I treat time a little bit different. But it is possible to write down the algebra group of the symmetry transformations. And once you know the algebra responsible for how special relativity works, you can write down or enumerate all possible representations of the symmetry group SO plus 3 column. So what does that mean? It means that you can make a systematic list of every type of particle that can ever exist in nature. When I make this list, I can write down particles that are spin 0, particles that are spin 1/2, particles that are spin 1, and even more than that. Because of the way that left and right-handed chiral symmetry gets mixed into the game, there are many ways to make a spin 1/2 particle. You might have a Dirac fermion, or you might have a Majorana fermion. Quantum field theory allows for many different ways to construct these types of particles, but there's only so many of them. And you can write them all down from start to finish. So that exercise in listing all possible field theories, all possible free field theories, gives us basically a menu for what we can build nature of. So our menu of particles includes things like the free scalar theory. The free scalar theory is the one we've been writing, 1/2 d mu phi minus 1/2 m squared phi squared. If I go to the spin 1/2 case, then I can write down the Lagrangian for the free Dirac field. That is psi bar I d slash minus m psi. And d slash here means the partial derivative d mu together with a set of gamma matrices, the 4 Dirac gamma matrices. Dirac gamma matrices. These things are 4x4 matrices that describe a spin 1/2 particle. Why is it 4x4? Because the spin up state and the spin down state can both have left and right-handed pieces. It doesn't really make sense unless you have the full discussion about chiral symmetry to go with it. But the reason that you get 4 is basically a product of 2 spin states up or down and 2 chiral pieces, left-handed or right-handed. You can even go so far as to write down the Lagrangian for the free vector field, which is minus 1/4 the field strength tensor F mu nu, where F mu nu is the derivative d mu a nu minus d nu a nu. There is a lot to be said about what happens when you start to include the vector terms, especially when the vectors start interacting with things. This is what takes us down the road of needing to understand gauge symmetry and what it has to do with constructing the Lagrangian of a vector field in the first place. But there's nothing in the world wrong with the Lagrangians of the scalar and the Dirac particles. These sidestep all of the pesky questions of gauge theories, but I can still develop all the techniques necessary to do quantum field theory. So without diving yet into all of the complications of a gauge theory, we can talk about interacting theories in terms of the scalar and the Dirac Lagrangians. So if those are what the free theories are like, the interacting theories, an interacting theory by definition has a nonlinear equation of motion, so that its solutions do not satisfy simple linear superposition. That means that they typically have terms in the Lagrangian which go like the cube of the field or higher. Interaction terms of higher order in the fields. And standard examples of interacting theories that you can construct out of the scalar and the Dirac Lagrangians include so-called phi cubed or phi to the 4th theories. So I can take the scalar theory and make a phi cubed theory out of it by adding a nonlinear interaction term. Such as minus lambda over 3 factorial, which is just chosen for convention, phi cubed. That phi cubed means that it's going to turn into a phi squared in the equation of motion, and I'll have something nonlinear. This is sort of a boring Lagrangian where there's only one type of field, one type of particle, but that particle can interact with itself in a tricky way. A more interesting case is the Yukawa theory Lagrange. Yukawa theory is a mixture of both the scalar and the Dirac Lagrangians. So it has both the free scalar parts and it has the free Dirac parts. But the thing that's unique about it, the interesting part that makes it interacting, is that it has a vertex that couples the two together. Minus G psi bar psi. What does that mean for our interacting theories? It means that those nonlinear interactions will change the solution in a significant way that you can't necessarily solve exactly. So if my original free scalar theory looked like a scalar particle created at point X that goes off to point Y, when I turn on this kind of interaction, my particle starts to interact with itself. So the interaction is capable of changing boring vacuum propagation from X to Y and allow this particle to interact with itself. So I might have a vertex where I create another particle and a second vertex where that particle interacts with itself. This is one type of self-interaction that can happen in phi cubed theory. And a general interacting theory would include all possible combinations systematically in a small parameter. Typically, you want to do it in perturbation theory, order by order in a small coupling constant. Similarly, for Yukawa theory, I introduce a vertex of this type. The interesting thing about Yukawa theory is that there are multiple types of particles. So this correction allows me to start with, say, an electron traveling from point X to point Y. And the corrections to that in the interacting theory can involve the electron talking to itself by the interaction with a scalar field. So this is a self-interaction of the electron where a quantum fluctuation allows it to momentarily radiate a scalar field. And then later on absorb that same scalar field. And if I continue to add more and more interactions from the interaction term, I get more and more complicated diagrams. So typically speaking, when we try to solve problems in perturbation theory, this is the approach. Typically, we assume that the coupling constant, in this case G, or in this case lambda, is very small. And we assume that I can just limit myself order by order in perturbation theory to, let's say, the order lambda squared part, or the order G squared part. And I'm allowed to stop the series because in a weak coupling perspective, everything which is higher order is even smaller than what I've kept. That's supposed to be the philosophy of perturbation theory. Maybe a good place to stop is for me to point out where that breaks. One of the dirty little secrets of quantum field theory, or any quantum mechanics for that matter, is the ways that perturbation theory frequently fails. So one very famous example of the failure of perturbation theory is a genuinely non-perturbative effect. So here I take an example from a totally different branch of physics. This is from superconductivity. The BCS theory of superconductivity gives you this expression for the binding energy of a Cooper pair. This is how much energy it takes to break apart a Cooper pair in the superconducting state and have free electrons that can then. The various factors on the right-hand side are the Debye mass, the density of states at the Fermi energy, but the thing that I really care about here is that potential, V0. This is my coupling constant. That tells me how strong the effective attraction between two electrons is in the BCS theory. You would like to do this in a weak coupling perspective, calculated in perturbation theory, where I expand if V naught was very small. The problem is that this function, e to the minus 1 over V naught, is sick. It does not have a Taylor series. So unlike a normal smooth function where I can do the Taylor series, I can expand it, take the first derivative, take the second derivative, and then set V equal to 0. Something really screwy happens for a function of this type. You see what happens if you put V to 0 immediately. You get e to the minus 1 over 0, which is infinity, right? I get something that blows up. I get 0, e to the minus 1 over infinity. No, I keep saying it backward. I get e to the minus infinity, I get 0. And I get 0 no matter how many derivatives I take. So this first term in the Taylor series is 0. But then if I take some derivatives, I get a polynomial times the same function back. And the singularity when V naught goes to 0 from this kills anything that I get in front from derivatives. So the point is that that singularity goes to 0 so fast, everything is 0. Every single term in the Taylor series is 0. This kind of singularity is called an essential singularity. It's a 0 that is so strong that it overwhelms the Taylor series. And that means that this function has no series expansion around 0. Even though we would like it to, this form just doesn't have a Taylor series. So that's the first way that perturbation theory can fail. Sometimes there are effects in physics that simply do not have a Taylor series. Those are effects that are not perturbative. If you try to do a series method, a perturbative method, to look for BCS superconductivity, you will never ever find it. It is only possible to find it as a non-perturbative effect. And if you frame your question in terms of perturbation theory, it just won't appear. You're going to get 0 plus 0 plus 0. So at least for myself, everything that I'm going to tell you this week about quantum field theory is using perturbation theory. But I have to be honest about this caveat. Perturbation theory can only get you so far. There are always fundamental physical effects that can appear that just don't have a perturbative correspondence. These are these essential singularities, and they come from fundamentally non-perturbative things. Typically, those are radical transformations of the degrees of freedom in your problem. That happens when you have a phase transition. So it makes sense that that happens in BCS superconductivity because at high temperatures, you have a normal metal. But at low temperatures, you have a complete transformation of the degrees of freedom. At high temperatures, your degrees of freedom look like electrons and holes. But at low temperatures, the degrees of freedom change to become Cooper pairs. The exact same thing happens to QCD. At high energies or short distances, the degrees of freedom of QCD are quarks and gluons, where I know what the Lagrangian is. I know how to do a perturbative calculation in terms of quarks and gluons. But the thing that I cannot do in perturbative QCD is solve for the ground state. Because QCD has a phase transition at low energies, the chiral phase transition, which changes the degrees of freedom of nuclear physics from being quarks and gluons at high energies to protons, neutrons, and nuclei at low energies. That phase transition is a non-perturbative effect, completely analogous to this essential singularity in BCS superconductivity. So perturbation theory has hard limits on what it can tell you. Perturbation theory has the degrees of freedom baked into it. And if those degrees of freedom collapse, then perturbation theory is no longer accurate. There's a lot of things that you can do in perturbation theory if the change in the degrees of freedom is slow enough. So that's probably where I will start next time with the idea of logarithmic resummation. That if the perturbations, like if the degrees of freedom change too quickly, then perturbation theory breaks. But if the degrees of freedom change slowly, then you can change your perturbation theory along with it. This is the basis of the idea of resummation. And that's going to have everything to do with the techniques that we will use to study the physics of QCD at high energies or small x, and that's going to lead to ultimately gluon saturation. Okay, 2 hours has really flown. Thank you very much for sticking with me. Again, apologies for the format, apologies for starting at a very basic level, and apologies for going very quickly. I hope now that we're in the level of talking about quantum field theories, that next class I'll be able to finish the construction of QCD itself. And then we can start talking about properties of QCD and doing calculations. Thank you very much. What questions can I answer?
Not necessarily a question, but thank you for staying up till 1 a.m. to give us lectures from across the sea.
You are very welcome. I'm going to go collapse in my office and sleep for a few hours.
You have a few quick questions, one or two maybe.
Yeah, absolutely, please.
Yeah, Matt, let me ask you a question. So, hey, how's it going? So, you did this very nice job of motivating that there are certain essential singularities that perturbation theory might miss. Are there situations where, and in fact, it almost suggests in your example that you don't even know from perturbation theory that you're missing the singularity. So I'm wondering if A, like, what are some signs that we might be missing some important physics? And then, B, how can we find them? Maybe when, for example, expanding around a slightly different point.
Beautiful.
And we miss something.
Yeah, thank you. So excellent questions, and you set me up wonderfully for the next topic. In general, I think you do not have a robust way of guaranteeing that you have found all possible non-perturbative effects. I think the story of BCS superconductivity is very illustrative for that. At the time that Yoichiro Nambu discussed spontaneous symmetry breaking in BCS theory and how it relates to spontaneous symmetry breaking of chiral symmetry and high energy theory. There was exactly this discussion of why is there a mismatch in two different calculations of BCS theory. There was a calculation by, I want to say it was Cooper, and then there was a separate calculation by Nambu, and they both disagreed on something related to gauge invariance. And the two had to go way deep into the weeds to clash to understand why am I getting two different answers for what should be the same theory. And the reason is because there was a missing non-perturbative contribution that Nambu found that, if I recall the history correctly, that Cooper's paper had missed. So there was a deep connection there where if you pose the problem in a perturbative way to start off with, you don't have a way to guarantee that you found such essential singularities that have no perturbative counterpart. In that case, the signature that something was missing was a breaking of gauge symmetry. So you can use symmetries perhaps as an indication of whether something is definitely wrong or not definitely wrong. Doesn't mean that everything is right, but I don't know, there are other tests that one can do in terms of sum rules or unitarity that might give you some indication whether there's something missing. But as a general rule, I would say probably you don't have a foolproof way of telling whether there is a non-perturbative contribution that you might be missing. But if the degrees of freedom change slowly instead of suddenly, it's really that phase transition problem that's at the root of these non-perturbative effects. But if what you have is a smooth crossover and not a total breakdown of your degrees of freedom all at the same point, then you can essentially phrase it as perturbation theory, but about a different ground state. And that's exactly the perspective that I'll take when we're doing resummation. So for example, the vacuum QCD, which is where we'll start probably next time, does perturbation theory starting with an empty vacuum. And you count one quark, one gluon, two quarks, one particle at a time. When I do the resummation of all of the effects that are relevant at very high energies, where I have radiation of huge numbers of gluons that leads to gluon saturation, the answer that comes out of that is still perturbation theory, but it's perturbation theory starting with the classical equations of motion, the classically high occupation numbers of the gluon field, not starting with the empty vacuum. So it is still perturbation theory. It is still order by order, but you've moved the starting point. And that ability to move the starting point for perturbation theory, if the change is sufficiently slow, is exactly what resummation does for us. So thank you for the questions. I hope that we can come back to that again after we've discussed resummation next.
All right. Thanks again. let's have a bit of a break, right?
Thank you so much.
Before we come back here, you've all seen the timetable, you know when you have to be back here. There is tea and not very fancy coffee across in the Duncan Elliott room. Please